Hello, and welcome to EEE 174 CP 185 Instruction into Hand Assembly. So this video we're going to be covering how to do hand assembly for the lab class, as well as what handouts we need to look at and how to fill out the hand assembly template chart. So where to get these documents is you go into Moodle and you can download the x86 lab files, and what we're going to need is the hand assembly template as well as the hand assembly instruction handout. And these are the two main ones we're going to use throughout the entire video. So as you can see here, I already filled them out for time, so that way the video is not very long. But I already filled out some of the key components. So if you can go ahead and do this whenever you feel free, or pause the video. You want to fill out the instruction, the address, the operation, the destination, and source. And you fill it out basically with this following information. And for this video, we're just going to cover the first couple set of instructions to the first JGE, or conditional jump greater equal than. So the first instruction we're going to cover is the move DX to 0120, and this is an immediate to register operation. So as you can see here, I filled out the following information, and how do we figure out what this is in binary is first we want to find out the instruction format. So we go to our hand assembly instruction handout, which was again those x86 lab files, and we want to click this, and we're going to move all the way to the bottom of the document. Once there, we're going to go to the move section here, and we want to look for immediate to register. Now you see here there's an immediate to register and immediate to register with alternate encoding, and for this purposes of this we're actually going to use the alternate encoding because it reduces the size of our hex and instruction size. So we're going to go ahead and type out first the data that's relevant. So we're going to go 1011, the W, reg, and immediate data. Okay, so we have a couple unknown variables or variables that we need to fill in, which is W, reg, and immediate data. So our W, we're basically going to first scroll back to the beginning of the document for the instruction handout. And we can see here in table B3. So we're dealing right now with our 16-bit register DX. So our W is going to be regarding the width of our registers that we're using, and if W is equal to 1, we're dealing with the 16-bit registers, and W is equal to 0, we're dealing with the 8-bit registers. So in this case, we're dealing with the 16-bit, which so means W is equal to 1. And the register field is regarding the same table. So if we go here, we look for DX. So we're in again width, W is equal to 1 width, and we're going to go to DX. We go across, and we see our reg is 3 bits wide, and it's 0, 1, 0. And from there, we're going to fill in the immediate data. Now, the immediate data, when we fill this in, this system is again x86 architecture, which is Little Endian. And when we need to do this, we're actually going to swap the byte order, or swap the bytes. So we're actually going to put 2001 for the hex value, which is our immediate data 0120. So now we're going to fill this information all into binary first. So we're going to go 1011. Our W is equal to 1. Our register, our register is equal to 010, and our immediate data is in hex 2001H. Excellent. So we have here is B in hex, right? This is A, and then 2001. So our whole instruction should be BA 2001. Now, I'm going to double check just to make sure I filled it out correctly, and see here as we look in our listing file, the instruction is BA001. Excellent. So next we're going to move down to the next instruction, and the next instruction is the move AX to memory, the move whatever's in the contents of memory location 200 to register AX. So first we want to find out where this instruction is going to be. So we go down to the address, and now we started our original program at memory at the location 100, but we need to figure out where this one is going to start. And how do we solve this is by looking at the instruction size. So we can see that how many bytes is this. So we go 1, 2, 3. So it's 3 bytes. So that means adding 3 bytes to 100 means we're going to address 103. Excellent. So the instruction move AX to memory location, or I'm sorry, move 200, whatever's at memory location 200 to AX. To find out the instruction format, we're going to scroll down, again, back to the table to the move instruction here. Now, you notice here I put memory to register, but when I look at this table, I actually have another option besides memory to register, is I have memory to AL, AX, and EAX. Now, because AX is a special register for this operation, it has a different encoding. So I'm actually going to use the special encoding because it decreases, again, the size of the bytes, and it makes it a little bit easier when you do hand assembly. You don't have to deal with too many different unknown variables. So I'm actually going to change this instead of register to AX. And from here, I'm going to fill in my instruction format, which I find from here right across. So that's going to be 1010001 W, and then full displacement. Okay. So for my unknowns, I have W and then full displacement. And we'll talk about full displacement in a second. But first, let's fill in the binary. So we're going to go 1010. Then we have, oh, helps if I fill in that other one. Then we have 001. And again, our W value is a 16-bit register, so it's actually going to be equal to 1. So, boom. Right? And then now our full displacement, what we're going to enter is just simply the memory location of where we're going to look at. Okay, now remember, this is Little Endian, so we want to put in the values in Little Endian, which is reverse byte order. So we're going to put 0002 in hex. And I'm going to put hex there because I'm not going to write it in binary just to save time. And then out from there, we look at the instruction and we convert it into hex. So 1010, right, which should be A. And we have 111. Double check that. Oh, sorry. There's supposed to be, make a small correction here. It's always good to double check yourself when you do this. It's actually, the instruction is not that extra 1, but it's 3 zeros. There we go. Excellent. That fixes it. So we look here. Again, when I made a mistake, I looked here and I looked at the wrong one here. So be very careful about that. Make sure you look at this first instruction. And that's actually just 1, right? And then we put in the hex. Boom. So altogether, instruction should be A1, then 3 zeros and 2. Now again, we want to double check ourselves. We're going to go back. We're going to look at the listing. We go A1, 0, 0, 0, 2. Excellent. So far so good. Now we're going to go to our next instruction. Move BX 0202. So this one, we look here, and there's no special encoding for memory to BX. So we're going to have to use that memory to register. So first thing we're going to do is we're going to write out the format of our instruction. So 100, and then from here, it's memory to reg, so it's going to be 101 W mod reg r/m. So this instruction, we have quite a few different unknowns. So for this, we have W, we have mod, we have reg, and we have r/m. Okay? Fill these in a little bit. Excellent. Oh, and before I forget, we actually should make sure we put in the address. So, again, how we solve for where this is located for this instruction is we look at the previous instruction, we look at where it was an instruction pointer, or where it's instructed, where the address is located at, and we count the number of bytes of that instruction. So we have 1, 2, and 3. So we're going to add 3 to 103 in hex. So remember, we're talking about in hex, and so we have 106. Boom. All right. Sorry about that. Let's go back to this instruction. So now we need to solve for W. So again, we know what the width is because we're using BX. So it's going to be equal to 1 mod. We'll talk about mod in a second, but let's look at the reg first. So we're going to go back to our document, and let's go all the way back up to table B3. All right, so our W is 1, and we're dealing with BX. So we're going to go down the table, we look for BX, and we go across for 0, 1, 1. So that's for reg, so 0, 1, 1. All right, so the field encoding. So this is the next unknown variable. So this one I'm just going to tell you for now for the lab. We're just going to enter mod 00. And you're going to do this for a lot of the lab. Unless otherwise stated, we'll explain. You can talk to your lab instructor and they can go into greater detail what it is. But for making sure this video isn't too lengthy, we're just going to keep it a little simple. Okay, for our next table, we go down to mod 00, and from here we go down to the direct address, and we're going to use the r/m or register/memory field encoding to 110, and we're going to fill in that part right there. So space 110. Okay, so we have, for the most part, most of our information. So we're going to start filling in some of the binary, and it's always important when we do this to go from left to right, and you'll see why in a second why this becomes important. But from here, just always start from left to right. So from here, we're going to go from 1000. Okay, then we have our next set, which is 101, and then our W, which is 1. Now from here, this is why it's important to start from left to right. We look at the mod and the reg. Mod is only 2 bits wide, and the reg is 3 bits wide. Well, to represent a nibble, we need only 4 bits. So what ends up happening is we're going to use the first 2, which is starting from left to right, the mod, which is 2, and then we're going to use the most significant 2 from reg, and then carry over the last bit from reg over to rm. So we have an even number of 4. So we're going to start out again with the mod variable from left to right. So we go 0, 0, and then we're going to put the 2 most significant bits from the reg, which is 0, 1. Okay? So again, the first 2 zeros are 0, 0 from mod, and then the next 2, 0, 1, comes from the most significant 2 bits from reg. So that's how we get 0, 0, 0, 1. Now from there, the next one, we're going to put the leading 1 from reg, so the least significant bit in this case, shift it over, so we go 1 from reg, and then we have 110 from r/m. And that's how we determine those values. So it's really important to know that we go from left to right and then start adding the variables in. Now the other thing we didn't talk about here, but it's down here, is the direct address. So we're going to include that. And to do that, we're just going to include 0202. And again, when we do a little Indian of that, when we swap it, it comes out with the same exact value. So not too hard there. So we're going to go 8 B 1 E and then 0202. So from here to fill it in, all together we're going to have 8 B 1 E 0202. So again, we're going to double check that. So I'm going to go over, and yes, that is correct. Okay. So the next instruction we're going to do sub AX comma BX, which is a subtraction operation. So we're subtracting AX from BX and storing it back into AX. Now, to do this one, we're actually going to work a little backwards. We're actually going to go from the hex and work our way up, just so we can do that once, so we can see how the process can be done. Now, first though, we're going to remember to put the address, so we need to figure out what that is. So again, we're going to take our current address from our previous instruction, so 106, and add the size of the value. So you have 1, 2, 3, and 4. So 4 plus 106, again, and this isn't hex, is actually 108. Okay, so now we're going to work backwards. So I actually provided the hex, and where I got this, you're wondering where, is from the listing file. So if I look at the subtract, and I got 29D8. So I filled it in, you got the binary, and what I'm going to do is I'm going to scroll down to the table, and I'm going to look for subtract. Boom. Okay, so we know it's a register to register operation, but when I look here, I see 2 different ones. So how am I going to do this is I'm going to first look across the binary, and I see that the encoding that the first one, 0010, is a hard-coded value, so it's provided, but the next one is where it changes. So we have 100W. Well, if we know W is equal to 1, then we know it can't be this, right? Because 101 would be a different value than this. So this is what matches. So that must mean that we're using a register 1 to register 2 operation, right? So I'm going to just fill in this information, W equals to 1, because we know it. Now, the next information we need is register 1, right? And register 2. So now that we got this information, though, for which encoding we're using, we know which one is register 1 and register 2. So we know 1 is hard-coded. So when we look at this next nibble here, we're going to ignore this 2 leading 1s, and we're going to go to the next 2 binary digits, and we have 0, 1, and then we look over to the most leading because we need 3 bits for register. So remember, register is a 3-bit wide variable, and it's 1. So our reg 1 is actually 0, 1, 1. And now we'll look at reg 2, and all that's left is 3 zeros. 1, 2, 3. Excellent. So now we want to make sure that we figure out what reg 1 and reg 2 is, right? I'm going to widen this out so it's a little more visible. So I'm going to go to my table, and we're going to go back to that table B3. Boom. All right, and now we look here and we say, okay, well, we need to figure out what reg 1 and reg 2 is, so we make sure we enter the right one for going in backwards. So we look here and we see 0, 1, 1. So I go down, 0, 1, 1. And I go all the way across, and W equals 1 is BX. So that means reg 1 is actually BX. And if I look here, 0, 0, 0 is AX. So reg 1 is BX, reg 2 is AX. So it's a way we can work backwards with our encoding, and it makes it a good way, especially for lab 1 part 2, when you don't know exactly how to encode an instruction or how they encoded it, to figure out which encoding or which format was used to do it. So the last instruction we'll cover for these sets of videos, or video, will be the conditional jump. So first, we want to fill out the address. So in order to do that, we're going to take our previous address, which is 10A, right? Oh, not there, though. We're going to take 10A and add the size in the instruction. So 10A, it's 1, 2, so it's 2 bits wide. So we're going to add 2 to 10A, right? Which gives us 10C. Excellent. So we're at 10C. So now we have to figure out how do we do a conditional jump. And once you figure out how to do a conditional jump, unconditional jumps are very much the same way. They're actually a little easier. They're just a little easier because they have no unknown, or one less unknown, I should say. So when we do conditional jumps, we're going to look for the JCC, jump if condition is met. And for this lab, for the most part, we're only going to use the 8-bit displacement for the jumps, okay? And this is really important. And you can do the same thing for jumps, the unconditional jump to the same segment. Just go ahead and use the 8-bit displacement, or the short jump in this case, okay? So, but for this one, we're going to do JCC, and we're going to go ahead and type out the format. So the format is 0, 1, 1, 1, and then we have another unknown variable called TTTN, and then you have your 8-bit displacement. Okay, so our unknown value is TTTN, right? And to figure that out, we're going to go back to our hand assembly instruction handout, and we're going to go ahead and scroll up to one page above to table B8. And we have this table here, and we're going to go down and we're going to look for GE, because J is just a constant jump, and we want to see if our condition is. So we look here and we say GE, and we look across to figure out our TTN value. And we see that our GE is, or TTN for GE is 1101 for greater than or equal to. So I'm going to enter that, 1101. Okay, so far we have 0, 1, 1, 1, and then we have 1, 1, 0, 1. Excellent. And if you remember what the value was before, 7, and then it should be, I believe, D. Double check myself. Yes. All right. So the next part, the 8-bit displacement. This is one of the trickiest part about conditional jumps. When we do 8-bit displacement, we want to do is we're jumping relative to our current location. So either forwards or backwards or forwards. So how do we figure this out? So basically, we're going to take where our current address is, and we want to say, I want to jump to location 114. Okay? So how do I figure that out? Well, I'm going to go ahead and just use my handy-dandy calculator just to make my life a little easier. And if you didn't know this, Windows Calculator has a fantastic programmer calculator. And I'm just going to simply go here, and I'm going to plug in 114 into my hex, subtract 10C. And I come out with 8. So you want to put the relative jumping the distance away from 8. Now, I'm going to put this in hex. So keep in mind, if I want to jump backwards, I'm going to do the 2's complement and find the negative value. Now, I'm going to double check this. And what we see is, wait a minute, it's 7D06, but I'm 8-bit bytes away. Well, the reason why is we need to take into account the size of the instruction. And the instruction overall size will actually be 2 bytes. So I need to subtract 2 bytes from 8, which should give me 6. And that leaves my final answer, 7D06. So remember, when we do conditional jumps, or even unconditional jumps, if you're doing the 8-bit displacement, you need to include the size of the instruction, which is 2 bytes. Okay? So that's very important. And this also is as well as in the fact if you jump backwards in the 2's complement, you need to make sure you take that into account as well. So I hope you enjoyed the video. We've covered the first 4 instructions. This is a good step into how do we do hand assembly in the lab class. And if you have any questions, feel free to contact csusiee@gmail.com about the video if you think there's something missing or more that can be added. Or you can feel free to talk to your lab instructor. He probably can go into, or she can go into greater detail about what process is done or any additional information that you wish to hear.